Good evening and welcome to a new course about systems of ordinary differential equations. Tonight we'll look at the remaining case when the matrix of the system is not diagonalizable. So we'll look at this new notion called the Jordan form of a matrix and use it to solve systems of linear equations with constant coefficients in the case when the matrix of the system is not diagonalizable. So to recapitulate what we have gone over so far, if you have a system of ordinary differential equations that are linear with constant coefficients, you can write it in matrix form as y prime is equal to ay plus b, where y is a vector, a column vector with n components, each of which is one of the unknown functions, and A is the system matrix, the coefficient matrix, which is an n times n square matrix corresponding to n equations with n unknown functions. And B is the source term. If B is constantly 0, then the equation is homogeneous. If B is a non-zero vector, then the equation is called inhomogeneous, or the system is called inhomogeneous. And we impose some initial condition, y at time t0 is equal to y0. So y0 is a vector made of the initial conditions for all the unknown functions at time t0. All right, so then the system can be solved by using this formula, which is the same as the formula that we would use in the case when we are dealing with one linear equation with constant coefficients. Y of t is equal to the exponential of a times t minus t0 applied to y0 plus integral from t0 to t of the exponential of a times t minus s applied to d of s integral ds. So the difference is that in the system case, y0 and d of s are vectors, and the exponential is a matrix exponential, and the integral is the integral of this vector valued function. Anyway, the main difficulty in this computation is computing the matrix exponential. When the matrix when the system matrix is diagonalizable, meaning that A is equal to C, D, C inverse, where D is a diagonal matrix, C is an irreversible matrix called a change of basis matrix, and C inverse is the inverse of C, then we can use this to compute the exponential that appears in the previous formula, namely the exponential of AT is C times the exponential of dt times C inverse. And the exponential of a diagonal matrix is computed by taking the exponential of all the eigenvalues on the diagonal. So the exponential of dt is the diagonal matrix with e to the lambda 1t, e to the lambda 2t, etc. up to e to the lambda nt on the diagonal. If D, the original diagonal matrix, which is called the diagonal form of A, has the eigenvalues lambda 1 up to lambda n on the main diagonal. Unfortunately, that formula does not always work because not every matrix is diagonalizable. So let's give an example of a non-diagonalizable matrix and prove that it is not diagonalizable. And then later in this course, we'll see how to compute the matrix exponential in this case. So first, let's try to treat it as if it were diagonalizable, try to diagonalize it, and then prove that this is impossible. So first, let's find its eigenvalues. In order to find its eigenvalues, we need to find its characteristic polynomial. So we need to find the trace and the determinant of the matrix. So trace is the sum of the values on the main diagonal. So it's 2 plus 0, which is 2. And the determinant is 1. So the characteristic polynomial is lambda squared minus 2 lambda plus 1. So lambda squared minus the trace of the matrix times lambda plus the determinant of the matrix. It's slightly more complicated for larger matrices, but this is how it works for 2 by 2 matrices. And lambda squared minus 2 lambda plus 1 is the same as lambda minus 1 squared. So this has a double root 1. Both roots are 1. So this means that A has both eigenvalues equal to 1. Then if A were diagonalizable, then A would be equal to C D C inverse, where C is the change of basis matrix, and D is the diagonal form of A, which is the diagonal matrix with the eigenvalues of A on the main diagonal. But the eigenvalues of A are both 1, so D is the matrix with 1 on the main diagonal and 0 off the main diagonal, which is the same as the identity matrix. So D is the identity matrix. So in that case, A would have to be equal to the change of basis matrix C times I, which is the identity, times C inverse. But any matrix times the identity is equal to the original matrix. So C times I is equal to C. So this is the same as C times C inverse, which is the identity matrix I by definition. But clearly, the original matrix A is not the identity matrix. So this means that it is not diagonalizable. So in general, for size 2 square matrices whose 2 eigenvalues are the same, either they are a multiple of the identity matrix, which is proved the same way as on the previous page, or they are not diagonalizable. In higher dimensions, this is more complicated, but so this means that for 2 by 2 matrices, we have an easy way to recognize when they are diagonalizable and when they are not. So if a matrix has, if a 2 by 2 matrix has a double eigenvalue, so if the 2 eigenvalues are the same, and if it is not just a multiple of the identity matrix, this implies that it is not diagonalizable. And if the 2 eigenvalues are different, so if lambda 1 is not the same as lambda 2, this implies that the matrix is diagonalizable. So it's a pretty simple classification for 2 by 2 matrices with only 3 cases. Either the matrix is diagonalizable and its eigenvalues are different from each other, or the matrix is a multiple of the identity matrix, so lambda 0, 0, lambda, or the matrix is not diagonalizable. So now we're going to see how to handle this situation when the matrix is not diagonalizable. It turns out that there exists a more general notion instead of the diagonal form of a matrix, which is called the Jordan form of a matrix. So even though not every square matrix is diagonalizable, every square matrix can be brought to its Jordan form. So there exists a change of basis matrix C and a Jordan matrix J such that A is equal to Cj C inverse. And we're going to define what a Jordan matrix is, and we're going to use this to compute the matrix exponential of the matrix A. So a Jordan matrix is somewhat more complicated than a diagonal matrix. A diagonal matrix just has eigenvalues on the main diagonal, which may or may not be zero, and is zero everywhere else. A Jordan matrix has some square blocks along the main diagonal and is zero everywhere else. But these square blocks don't have to be one by one. So if that were the case, the matrix would be diagonal. These square blocks, though, can be bigger. They can be 2 by 2 or 3 by 3, any size. So Jordan matrix has square blocks along the main diagonal and is zero everywhere outside these square blocks. For a Jordan matrix, these are called Jordan blocks and they have a special form. So a Jordan block is a square block with some number lambda on the main diagonal, which is the eigenvalue that corresponds to that block, and 1 on the diagonal immediately above the main diagonal, and 0 everywhere else. So 1 by 1 Jordan blocks are just one entry containing the eigenvalue. So if all the Jordan blocks are of size 1, like this, then it's actually a diagonal matrix. But there are also 2 by 2 Jordan blocks, which look like this, lambda 1, 0, lambda. So lambda on the main diagonal, 1 on the diagonal immediately above the main diagonal, and 0 everywhere else. What about 3 by 3 Jordan blocks? So again, for a 3 by 3 Jordan block, it has 3 lambdas along the main diagonal, 2 ones on the diagonal immediately above the main diagonal, and 0 everywhere else. 4 by 4 Jordan blocks, the same. So they have 4 lambdas along the main diagonal, 3 ones on the diagonal immediately above the main diagonal, and 0 everywhere else. So in general, Jordan block of size k is a square block that has k lambdas along the main diagonal, k minus 1 ones on the diagonal immediately above the main diagonal, and 0 everywhere else. And the Jordan matrix is a matrix that has these Jordan blocks along the main diagonal and 0 everywhere else. So here is an example. This is a Jordan matrix. It has 3 Jordan blocks, namely a size 2 block with the eigenvalue 0 here in the upper left corner, then a size 3 block with the eigenvalue 2, and one more block with the eigenvalue 0. So here I have used some colored shades to mark these blocks. So this 2 by 2 block here is a Jordan block of size 2 with the eigenvalue 0, and it's drawn in blue. Then this block here is a 3 times 3 Jordan block with the eigenvalue 2, and is drawn in red. And finally, we have a block of size 1, which contains the eigenvalue 0. And everywhere else, as you see, the Jordan matrix has zeros. So any diagonal matrix is also a Jordan matrix with all the blocks of size 1. So Jordan matrices are a generalization of diagonal matrices. And if all the blocks in the Jordan matrix have size 1, then it is a diagonal matrix. If it has some blocks of size 2 or higher, then it is just a Jordan matrix and it is not a diagonal matrix. Because any Jordan block of size 2 and higher has ones above the main diagonal. So in dimension 2, this means there are only 2 kinds of Jordan matrices. Again, it can only be a diagonal matrix with 2 blocks of size 1 along the main diagonal. So this means It has an eigenvalue lambda1 and another eigenvalue lambda2, which may or may not be the same. If they are the same, then this matrix is a multiple of the identity matrix, or it is just one size 2 Jordan block with the same eigenvalue on the diagonal and with a 1 above the main diagonal. So this is a Jordan matrix, and it's not a diagonal matrix in the second case. So if a matrix can be decomposed into C, J, C inverse, where J is a Jordan matrix, then the exponential of AT is C times the exponential of JT times C inverse. And the proof is the same as for diagonalizable matrices. So it is enough to know how to compute the exponential of Jordan matrices. And it turns out that there is a formula for this, which is not as simple as the one for diagonal matrices, but almost as simple. So the exponential of a Jordan matrix is also a block matrix. So it has square blocks along the main diagonal and 0 everywhere else, obtained by taking the exponential of each Jordan block. So for a size 1 Jordan block, then the exponential is what we have computed before. So the size 1 Jordan block consists of just one eigenvalue, lambda, and it's exponential. So if J1 is the block consisting of just one eigenvalue, lambda, it's a 1 by 1 matrix, then its exponential is e to the J1t, which is the 1 by 1 matrix consisting of e to the lambda t. For a size 2 Jordan block, so this has lambda on the main diagonal twice, and 1 above the main diagonal, and 0 in the lower left corner. Its exponential is e to the j2t. It has e to the lambda t on the main diagonal, t e to the lambda t above the main diagonal, and 0 in the lower left corner. So notice that the exponential of a size 2 Jordan block is also a size 2 block, but it's not a Jordan block. So it doesn't have 1 in the upper right corner. Anyway, so this 2 by 2 block is replaced by this 2 by 2 block when we take the matrix exponential. For a size 3 Jordan block, so this has 3 lambdas on the main diagonal, 1 on the diagonal immediately above the main diagonal, and 4 zeros to fill out the matrix or the block. Then its exponential is, well, it's again a 3 by 3 block. It has zeros below the main diagonal. It has e to the lambda t on the main diagonal. It has t e to the lambda t on the diagonal immediately above the main diagonal. So that's the same as size 2 Jordan block. And then in the upper right corner, it has t squared over 2 e to the lambda t. And what about for a size 4 Jordan block? So its matrix exponential is again size 4 block, but it's not a Jordan block. So it has e to the lambda t on the main diagonal, t e to the lambda t immediately above that, then t squared e to the lambda t on the diagonal above that, and t cubed over 3 factorial e to the lambda t in the upper right corner, and 0 below the main diagonal. So in general, one can use this sort of formula to take the exponential of any Jordan block, and therefore of any Jordan matrix, because it's just made of Jordan blocks on the main diagonal, So the exponential of a Jordan block has e to the lambda t on the main diagonal, t e to the lambda t on the diagonal immediately above that, and then t squared over 2 e to the lambda t above that, then t cubed over 3 factorial e to the lambda t above that, etc., and all the way up to, in the corner, t to the k minus 1 over k minus 1 factorial e to the lambda t. This is a Jordan block of size k. So this is a k by k block, and it is the exponential of a Jordan block of size k. And so this always has 0 below the main diagonal. So for example, for the Jordan matrix that I gave as an example earlier, that has a 2 by 2 block here in the upper left corner, so 0, 1, 1, 0, its exponential is 1t, 0, 1, because the eigenvalue lambda here is 0, and e to the lambda t then is 1. And t e to the lambda t is t, because lambda is 0, so e to the lambda t is 1. So this is the exponential of the upper left corner 2 by 2 block. Then the next block is the one that has size 3 and the eigenvalue 2. So the exponential of this block, again, I use the formula for the exponential of Jordan blocks of size 3. And this has e to the 2t on the main diagonal, t e to the 2t on the diagonal above that, and t squared over 2 e to the 2t on the diagonal above that. So just in the corner, just one spot, and 0 below the main diagonal. Right. And then in the corner, I also had one more eigenvalue, 0. So this is a Jordan block of size 1. And then the exponential of this block is e to the lambda t. Since lambda is 0, this is e to the 0, which is 1. And now the matrix exponential of the whole Jordan matrix has these blocks along the main diagonal, these 3 blocks along the main diagonal, and 0 everywhere else. So this is how one computes the exponential of a Jordan matrix. So let's use this Jordan decomposition to solve a system whose coefficient matrix is not diagonally zero. For simplicity, let's pick the same matrix that we had earlier and which we know is not diagonally zero. So let x prime equal to x plus y prime is equal to minus x, with the initial conditions, x of 4 is equal to 3 and y of 4 is equal to minus 1. Then letting y of t be the vector with 2 components, x of t and y of t. So it's a column vector with 2 components representing the 2 unknown functions. Then we can write the equation in matrix form as y prime, so dy over dt, is equal to a y, where capital Y here is this column vector, and the initial conditions are capital Y at time 4 is the column vector consisting of 3 and minus 1, so the initial conditions for the 2 unknown functions. And capital A here is the coefficient matrix, so the 4 coefficients are 2, 1, minus 1, and 0. So 2 and 1 come from the first line because we had 2x plus 1 times y. And minus 1 and 0 come from the second line because we had minus 1 times x and then no y. So this means plus 0 times 1. So 2, 1, minus 1, 0. The solution, if we write the system in this way, is very straightforward. So it's the exponential of a times t minus 4 times the initial condition y of 4. So this is a pretty simple formula, but now we have to compute the matrix exponential. So suppose we know that the system matrix A can be brought to its Jordan form, and after we do this example, we'll see exactly how a matrix can be brought to its Jordan form. But suppose that we knew it already, so A is equal to Cj C inverse, where J is the Jordan form of this matrix, and for this matrix, this Jordan form is 1, 1, 0, 1. So it's a 2 by 2 Jordan block with the eigenvalue 1. So, and no other Jordan blocks, because since this is a 2 by 2 matrix, there is no room for any other Jordan blocks. Okay, and the change of basis matrix is -1, -1, 1, 0. And then the inverse of the change of basis matrix, so C inverse, is 1 over the determinant of C times this matrix 0, 1, -1, -1. So please review finding the inverse of a matrix. And the determinant of C is 1. So it's just this matrix 0, 1, -1, -1. And then I actually checked, and it is true that C times J times C inverse is equal to the matrix A. So this was correctly computed. And I'll show you this computation in a couple of minutes. Then we can use this to compute the matrix exponential. So e to the at is c e to the jt c inverse. In general, for a size 2 Jordan block, so lambda 1, 0, lambda, its exponential e to the jt is e to the lambda t, t e to the lambda t, 0 e to the lambda t. In our case, lambda is 1, so the exponential is e to the t, t e to the t, 0, and e to the t. So then e to the at is equal to c times this exponential times c inverse. And I carried out the matrix multiplication in 2 stages. So in the end, we get that it's the matrix consisting of t plus 1 e to the t, t e to the t, minus t e to the t, and 1 minus t e to the t. And again, one way to check that this computation could be correct is to plug in t equal to 0. And when t is equal to 0, this should be the identity matrix. And let's check. When t is 0, we get 1, 0, 0, 1. And this does not prove that the computation was correct, but at least it shows it could have been correct. And it probably was. Okay, so then let's use this matrix exponential that we have computed and plug it into the formula for the solution. So we want y of t, which is e to the a times t minus 4, applied to y of 4. So we take the formula for the matrix exponential e to the at and replace t by t minus 4 because we want e to the a times t minus 4. So we get this expression, and we apply it to the vector y of 4, which represents the 2 initial conditions, 3 and minus 1. And doing this multiplication, we get a column vector with 2 components, as it should be. First one is 2t minus 5 times e to the t minus 4. Second one is minus 2t plus 7 e to the t minus 4. So the first unknown function, x of t, is 2t minus 5 e to the t minus 4. And the second unknown function was y of t is minus 2t plus 7 e to the t minus 4. And we have solved the system with these initial conditions by using the matrix exponential for a Jordan matrix. Just like for higher order ordinary differential equations, the fact that we have extra factors of t here, like 2t minus 5 and minus 2t plus 7, shows that we have some resonance. So the Jordan form is what happens when the equations of a system are coupled and they have two or more resonating modes. So the size of the Jordan block indicates how many modes resonate together. And they give rise to these extra factors of t or t squared or whatever else we'll get. But if we just have a system of two equations with two unknowns, then an extra factor of t is the most that we can get, because the Jordan block cannot be bigger than size 2. And in the exponential of a Jordan block of size 2, there is an extra factor of t. So this extra factor of t, like t e to the lambda t, or here in our case, t e to the t, shows that there is some resonance between the two equations. And finally, let's bring the system matrix to its Jordan form. So when I did the previous computation, I just said what the Jordan form is and what the change of basis matrix is. But now let's actually compute them and find them. And again, the Jordan form and the change of basis matrix are not unique, but we'll just find one Jordan form and one change of basis matrix. Actually, in our case here, the Jordan form is unique. Only the change of basis matrix is non-unique. But if there were several Jordan blocks, then the Jordan form will not be unique, because the Jordan blocks can appear in any order along the main diagonal. So first step, as always, is to compute the eigenvalues of the matrix A. And we already computed them once, and we get that the two eigenvalues are both equal to 1. So again, we first compute the characteristic polynomial. And the characteristic polynomial is lambda minus 1 squared. So this means that it has the double root 1. And as I said before, if a 2 by 2 matrix has a double eigenvalue, and if it is not just a multiple of the identity matrix, this means it is not diagonalizable. And this is somewhat more complicated for bigger matrices. Okay, so since this has a double eigenvalue and it is not diagonalizable, this means that this Jordan form will contain a Jordan block of size 2, corresponding to this double eigenvalue. So a Jordan block of size 2 is lambda 1, 0, lambda. Since this is a 2 by 2 matrix, this is all there is to it. There is no room for anything more. And the eigenvalue is 1, so the Jordan form will be 1, 1, 0, 1. All right. So in general, if an eigenvalue has multiplicity m, then the Jordan form of the matrix will contain Jordan cells corresponding to that eigenvalue of sizes adding up to m. So for example, if an eigenvalue has a triple multiplicity, so if it's a triple root, then it could correspond to Jordan cells of size 1 plus 1 plus 1, or 2 plus 1, or 3. Here, there are only two possibilities, so this is a double eigenvalue, and the only two possibilities are 2 and 1 plus 1. But if it has two Jordan cells of size 1, so 1 plus 1, this would mean that the matrix is diagonalizable, because a Jordan matrix that has only Jordan cells of size 1, then it is diagonalizable. Since it is not diagonalizable, then this Jordan form consists of one single Jordan block of size 2, because this is the only other possibility. So this is why in higher dimensions, this is more complicated, because there are more possibilities other than these two. Okay. So now we have found the Jordan form of the matrix, and we need to find the change of basis matrix. And unlike for diagonal matrices and for diagonalizable matrices, we will not look for two eigenvectors. Actually, it's impossible to find two linearly independent eigenvectors, but we'll look for one eigenvector and one principal vector. And we'll define what the principal vector is soon. So let's look for an eigenvector corresponding to the eigenvalue lambda equal to 1. As I said before, even though this is a double eigenvalue, we'll only be able to find one linearly independent eigenvector. So by definition, an eigenvector must solve the equation AV is equal to lambda V. And here lambda is 1, so AV is equal to V. Since this is a 2 by 2 matrix, its eigenvectors will have two components. So let V have the two components V1 and V2. Then we write the eigenvalue or the eigenvector equation. So the matrix, which is 2, 1, minus 1, 0, applies to the vector with components V1, V2 is equal to the vector with components V1, V2. So carrying out the multiplication, we have 2V1 plus 1 times V2 is equal to V1, and minus 1 times V1 plus 0 times V2 is equal to V2. So 2V1 plus V2 is V1, and minus V1 is equal to V2. Okay, so if everything was correct up to this point, then the two equations should be equivalent to each other, and they should have an infinity of solutions together. So if we subtract 2V1 from both sides in the first equation, we get V2 is minus V1, which is the same as the second equation, which says that minus V1 is equal to V2. So the two equations are equivalent to each other, and this system has infinitely many solutions, namely any vector such that the second component is minus the first component. So first, if the first component is some number A, then the second component is number minus A. And all of these are acceptable except when A is equal to 0. So we don't want to use 0, 0 as an eigenvector. But notice that these are all multiples of the same vector. So A minus A is equal to A times the vector 1 minus 1. So if they're all multiples of the same eigenvector, this means that we cannot pick two linearly independent eigenvectors. we can only get one eigenvector, which is what I said just now. So this means we cannot get two eigenvectors to use in the change of basis matrix. But at least we got one eigenvector. So let's make a simple choice like 1, -1, or -1, 1. So let's make the choice -1, 1. So we need a second vector for the change of basis matrix. And because we cannot use an eigenvector, we must use a principal vector. And this is a characteristic of Jordan matrices. So when they're bringing the matrix to its Jordan form, so we cannot use only eigenvectors. We cannot write the change of basis matrix using eigenvectors. We also have to use principal vectors. So the principal vector is is a vector u such that AU is equal to lambda u plus v, where v is an eigenvector. So this is similar to the equation for eigenvectors, but not the same. So if this were the equation of an eigenvector, I just have AU is equal to lambda u. That would mean that u is an eigenvector. Now this equation says AU is equal to lambda u plus v, where v is an eigenvector for the eigenvalue lambda. And we should use the same one that we already computed. And then for bigger square matrices, this gets slightly more complicated. So after we find the first principal vector, then we use the first principal vector in the equation to get the second principal vector. And then we use the second principal vector to get the third principal vector, etc. But so this was only if we have a Jordan cell of size bigger than 2. In our case, we have one eigenvector and one principal vector. And this is going to give us the change of basis matrix. So let's solve this equation and find u. So u is again a vector with two components. Let's call them u1 and u2. And then let's write the equation. So A times u, this means the matrix 2, 1, -1, 0 applied to the vector u1, u2 is equal to lambda u. Lambda is 1 in our case, so it's just u. So u is the vector with components u1, u2, plus v. And v is the vector that we had on the previous page, so vector with components -1, 1. And then if we carry out the matrix multiplication on the left and the addition of the vectors on the right, we get 2u1 plus u2 for the first component is equal to u1 minus 1 on the right hand side, and minus u1 for the second component is equal to u2 plus 1 on the right hand side. So now if everything was done correctly, then again, this system should have an infinity of solutions. So let's check. If we subtract 2u1 from both sides in the first equation, we get u2 is equal to -u1 minus 1. And similarly, from the second equation, if we subtract 1 from both sides, we get -u1 minus 1 is equal to u2. So it's pretty straightforward to check that the two equations are equivalent to each other. So the two equations actually reduce to just one equation, no matter how we want to write it. Maybe let's go with this. Minus u1 minus 1 is equal to u2. And this means we can just plug in any value we want for u1 and find u2. So as I said, it has an infinity of solutions. And let's make a simple choice again, instead of making something like 100 and minus 101 or whatever. Let's pick u1 to be minus 1, and then u2 is 0. So then u is the vector with components minus 1 and 0. So then the change of basis matrix is the matrix with these two vectors as columns. So the first is the eigenvector, and the second is the principal vector. So C is the matrix that has the first column with components minus 1, 1. So this is the eigenvector. And the second column with components minus 1, 0. This is the principal vector. So it's a pretty simple matrix because we made simple choices. And then A is equal to CJC inverse, where J is the Jordan form of A. So 1, 1, 0, 1. It's the 2 by 2 Jordan block with 1 on the main diagonal. And any Jordan block has 1 on the diagonal immediately above the main diagonal. So this third one in the upper right corner has a different nature from the other two ones. Okay. And the change of basis matrix again is minus 1, minus 1, 1, 0. And the inverse of the change of basis matrix is computed by using the formula for finding inverses of matrices. So this is how one brings a 2 by 2 matrix to its Jordan form. For bigger matrices like 3 by 3 matrices or 4 by 4 matrices, everything is more complicated, but it can be done in a substantially similar way. And finally, for completeness, let's prove that the exponential of a 2 by 2 Jordan block is given by the formula that I mentioned before. So if J2 is a 2 by 2 Jordan block with lambda on the main diagonal, 1 immediately above that, and 0 everywhere else. So here it just means 1, 0 in the lower left corner. Then its exponential is e to the J2t is equal to e to the lambda t on the main diagonal, t e to the lambda t immediately above that, and 0 in the lower left corner. Okay, so when proving this, we start from the definition of the exponential. So e to the J2t is by definition sum over all non-negative n of t to the n over n factorial times J2 to the n. So this is the power series that gives the exponential for matrices as well as for numbers. And then we look at this 2 by 2 Jordan block J2, and we write it as the sum of two things: the part that has lambda on the main diagonal and the one in the upper right corner. So the matrix that has lambda on the main diagonal and nothing anywhere else, so it's the matrix lambda 0, 0, lambda. This is just lambda times the identity matrix, where the identity matrix is the matrix 1, 0, 0, 1. And then we have this plus the 1 in the upper right corner. So we write this as a separate matrix, the matrix with components 0, 1, 1, 0. Let's call this capital N. So capital N also has some pretty special property, namely n squared is equal to 0. So if you compute the square of this matrix, you get that it's the 0 matrix. So the matrix with all entries 0. So since n squared is 0, then all the higher powers will also be 0. So we use this decomposition to compute j2 to the n. So to compute the powers of the Jordan block j2, because we need them in the definition of the exponential. So you write j2 as lambda times the identity plus n, and then j2 to the n is lambda times the identity plus n raised to the power n. And then let's use the binomial theorem to write this sum of two matrices raised to the power n. Notice that we can only do this for matrices when the matrices commute. So if you have A plus B to the n, and A and B are matrices, then you can only use the binomial theorem when the matrices A and B commute. And this is the case here. So this is the case because the identity matrix commutes with any matrix. This is because by the definition, even of the identity matrix times any matrix is equal to that matrix. So the identity times n is equal to n times the identity is equal to n. Okay, so then we are allowed to use the binomial theorem to expand this sum of two matrices raised to the power n. And we get that it's equal to sum for k going from 0 to n of n choose k, so the binomial coefficient, times lambda I to the k times n to the n minus k. But lambda I to the k is just lambda to the k times the identity, because the identity raised to any power is the identity. And almost all the powers of the matrix n are 0, because we established on the previous page that n squared already is 0. So n squared and all the higher powers are 0. So all the terms in this sum are 0, except for two terms, the one that contains n to the 0 and the one that contains n to the 1. So we get that this is equal to n choose n times lambda to the n times the identity plus n choose n minus 1 times lambda to the n minus 1 times n. So these are the only two terms that remain non-zero. And n choose n is 1, so we're left with lambda to the n times the identity. And n choose n minus 1 is n, so we have n plus n times lambda to the n minus 1 times n. Right, so then we plug this into the definition of the exponential, and we get, so we get a sum with lambda to the n times the identity plus n times lambda to the n minus 1 times capital N for each power j2 to the n. So we split this into two sums, the part that involves lambda to the n times the identity and the part that involves n times lambda to the n minus 1 times n. The first part that has sum of t to the n over n factorial lambda to the n times the identity, this is nothing but e to the t times lambda times the identity. So this is the exponential of a number times the identity, and it's actually, so it's the exponential of t times lambda times the identity. And what about the second part? So here, let's have another look. So we have sum for n going from 0 to infinity, t to the n over n factorial, n lambda to the n minus 1 times capital N. So first we notice that when n is equal to 0, by definition 0 factorial is 1, so we have no problem with having 1 factorial here in the denominator. But when n is equal to 0, then this term cancels because it contains n times lambda to the n minus 1. So actually the sum starts from n equal 1. It's sum from n equal 1 to infinity of t to the n over n minus 1 factorial lambda to the n minus 1 times capital N. And then let's factor out a t, because now if we start from n equal 1, this means that t to the n always contains at least a factor of t. And we write it as t times t to the n minus 1. So now it's t times sum of t to the n minus 1 over n minus 1 factorial times lambda to the n minus 1 times capital N. And if we make a change of notation, so we denote this n minus 1 by n, then we have sum from n going from 0 to infinity now, because n minus 1 goes from 0 to infinity if n goes from 1 to infinity. Okay, and then we replace n minus 1 by n everywhere. So we have t to the n of n factorial times lambda to the n times n. But this sum is nothing but the exponential of t times lambda. So this is the power series that defines the exponential for numbers. And t to the n times lambda to the n is t times lambda to the n. So we have t times the exponential of t times lambda times capital N. So then e to the j2 times t is the sum of these two things. So it's e to the t lambda times the identity plus t e to the t lambda times n. So it's e to the t lambda times the identity matrix plus t e to the t lambda times this matrix n that just has a 1 in the upper right corner. And when we compute this sum, we get exactly the formula that I said we should use. So this is the proof. The proof is similar for Jordan blocks of bigger sizes. You don't have to know this proof. I just wanted to show you how it works, and so that you should know that all of these things can be proved by using elementary formulas and various facts about matrices and power series. Thank you for your attention, and we'll continue next time with a different topic. Thank you again.